Hello, in the previous video we have learned that if you have a conductor moving across a magnetic field, there's going to be induced EMF across the length of the wire. In fact, the magnitude of the induced EMF is given by the rate of cutting of flux. So the magnitude of the induced EMF is BLV. As for the direction, you can use your Fleming's right hand rule. Then you realize that this is the positive terminal and this is the negative terminal. Let me remind everyone of the BQV force. If you have an electron moving rightward in this magnetic field, it's going to experience a magnetic force that's downward. You can use your Fleming's left-hand rule. Now let's think about the moving conductor again. Let's say this is a metallic wire. What's in a metal wire? Lots of electrons, right? So as the wire is moving rightward, the electrons in the wire are also moving rightward. And since all of them are moving rightward in a magnetic field, all of them will be experiencing a downward magnetic force. Wouldn't that cause electrons to kind of accumulate at the bottom end? Wouldn't that make the lower end of this wire negatively charged and the upper end of this wire positively charged? Could that be the reason why an EMF is developed across the ends of the wire? Interesting, yeah? So let's follow this line of thought and see whether we can get the same formula for the induced EMF to be BLV. So we consider one electron here moving rightward and therefore experiencing a downward magnetic force. Use your Fleming's left-hand rule. So do all the electrons in the wire end up here, leaving the rest of the wire without any electron? No, that will not happen, yeah? Because once the bottom end becomes negatively charged and the top end becomes positively charged, there's now an electric field everywhere in the wire. And the direction of the electric field has got to be downward, from the positive terminal to the negative terminal. Which means this electron is now going to experience an upward electric force because it's negatively charged, yeah? So this accumulation of charges will stop once the electric field is strong enough that the electric force is able to balance the magnetic force. And when that happens, we have the final potential difference across this wire. So let's do the calculation. When magnetic force matches the electric force, BQV must be equals to Q times E. Cancel away the Q, we get BV is equals to E. So E is the electric field in the wire. But you have learned that the electric field strength is equals to the potential gradient. You learned this in the topic of electric field. It's very similar to the parallel plates where the electric field is uniform between the two plates. So instead of E, we can write it as induced EMF divided by the length of the conductor. Because the potential difference between these two ends is simply the EMF that's induced. So take the EMF divided by the length of this wire L, you get the potential gradient, which is the electric field strength. And now you see it, right? The induced EMF is indeed equals to BLV. So actually, we do not need Faraday's law to explain why there's an induced EMF when a wire cuts the magnetic flux. The origin of this induced EMF is actually the BQV forces experienced by the electrons in the wire. Alright, that's all. Ta-ta!